Yep, yeah. All right. Okay. If everything goes according to plan, because you give it a folder, that's a good path. Should get pretty much nothing. Solution Explorer here on the right-hand side. So to get Visual Studio, to be able to do anything, you need to give it a code file, and you need to give it a code file that's part of the project. So here is my solution called pointers. On the right-hand side, hopefully you can see that. Pointers is my project. There's no code in here, so there's nothing really to run just yet. So we're going to try to run it. All right, it's saying it's unable to start the program, pointers.exe, because there was nothing to turn from code into binary to actually execute. So you do need to be careful that you don't just, let me say, if you go to files, and let's see where, that's not the kind of memory I want. Whatever, that's wrong language. All right, if we go ahead and download some CPP file. Right, Visual Studio is interesting, doesn't want to drag, that's fine. We'll get there. There's not the downloads folder, try it again. Right, if we just open up a code file here, Visual Studio is an integrated development environment. So opening up code files, which are just plain text files, is certainly something it's capable of doing. But if I try to run this still, it says there's no code to run because Visual Studio isn't being told to do anything with this file. It needs to be in source files. So you either need to add an existing code file, if you're trying to add an existing code file, or add a new code file if you're running something from scratch. All right, so just C++ source file. Give it a useful name. Useful names are always good. And I will try to make sure my brain's working in C++ and not C. Right, IO stream, that's just input output stream. That's where all the basic stuff is. And I'm lazy. I like to use namespace standard and not say standard C out for everything, whatever your preference. Right? If you don't have the using statement, you have to do this everywhere with the scope operator, blah. Right? Good programming practices is something we'll point out here and there, but it's not the objective of the class. Programming is a third of the course, 25 to 33% of the course. All right. Other than the code being readable, that's the only thing that is a requirement for use of mini code. If I can't understand what's going on because your white space is atrocious, right? You copied it to Canvas, you downloaded it from Canvas, you copied it back over from switching computers or whatever, and the white space has gotten ridiculous. Right, so just keep it a little bit clean and we should be good to go. Try to observe some reasonable naming conventions. You know, ABC are bad variable names, XYZ are bad variable names unless you're doing Cartesian coordinates. Everyone sort of with me so far? Anyone thoroughly lost? Fallen in a ditch? You guys are gonna have to tell me the meaning of the duck. I'm out of tune with what's going on with that one. There is no meaning. Sure, okay. We'll roll with that. No meaning. Oh, the duck noise. Okay, I remember now. Yes, I remember duck noise. Okay. All right. Pointer. See if it's going to like me doing that. C, C++ are a little blob out. All right, it's working so far. My new lines. All right, so before we get too deep, hello world, and you need to just go away, right? Integer variable, number 15, right? It's variable, location, memory, it has a value. Since it's a variable, it has location and memory. So our pointer variable, pointer, could point to number. Right, so right now, pointer is just point and null, as all good new pointers should do. So if I want my pointer to point to our number, we ask for numbers memory address with the ampersand operator, and we can go ahead and point to it. So when we're in a program again, we have an extra line of output. And now our pointer has a memory address that is meaningful. Through that memory address, right, let's go for this text, copy paste. We can go ahead and get the value through the pointer. All right, so our pointer is now coupled with number. Pointer has a memory address of number, so we can get to pointer, get to number either through number itself, as we did the first time on line 9, or we can get through it through our pointer, as we did on line 18. Right, so we printed out 15 at the end via the pointer, and we printed out 15 at the beginning via number. And so pointer is just a reference type variable whose job is to hold on to a memory address.
Can I ask a question?
Mm-hmm.
So for the second C out, your pointer is pointer. If that pointer is the address of the pointer?
Yeah, so the first 2 times we printed out pointer, right, we get a memory address because the value of a pointer is a memory address because it's a reference type variable. The last time we printed out, we put a star in front of it, which is the dereference operator, which means go to that memory address, treat the data that's at that memory address based off of our pointer type. So since we have an int pointer and I had an integer variable at that location of memory, it translated the bit pattern, formatted it as an integer, and then spat it out to the console.
Okay, got it. Thank you.
All right, so in our class, we won't pretty much be doing much of that. We will be dynamically allocate things such as dynamically allocating an array. So whenever you're using the new keyword gives you back a pointer, a memory address of where memory was allocated on the heap. And so a quick refresher, 2 primary areas of memory that an application is going to work with. One's the stack, where you stuff all the local variables, right? Number, pointer, anything that we defined inside the main function array, all those variables are stack allocated. They live as long as that stack frame allocates. I'll get your question in a second, Rohan. The other place we can allocate memory is on the heap. So whenever there's a new keyword involved, either you're calling a method, right? So just like malloc, calloc, realloc for C, or new for you and those of you in Java. The new keyword goes to the heap, calls the constructor if there is one, allocates enough memory for however big the footprint of that data type is, or array of that data type, as it were. Right, so if an int is a 4-byte data type and there's 10 of them, this is going to go allocate 40 bytes of memory and then tell me where it is. Because it's a memory address, we need to have a pointer. Right, so we can go ahead and say your array is, and then say array, and then we'll see similar things as we did before. It'll just be another memory address. When we get there, I think I have it still running from before. Let's try that again. Okay, Visual Studio, what's going on? Sometimes a rebuild is needed and sometimes a restart is needed. That already just broke the code. There we go. All right, so we've got our memory address. So array has another memory address we look at the values here, we see that they're very far away in memory. Right? It's because this value is a stack address and this value is a heap address. So completely separate areas of memory. And it's your question, why is int start pointer rather than, it doesn't matter. That's white space, right? You can, the white space here totally doesn't matter. I had a student, I don't know, 15 years ago say, it makes more sense to put it on the int because we're changing the data type. And then I was like, that completely resonated with me. So yes, we're changing the data type of the variable. So it makes more sense to have the star next to the data type than it does next to the pointer. But yeah, those are all, we can change the white space, space in between them, no space, space between pointer 1, pointer 2, and we can do a complete smash it all down to nothing. Right, that is just a space. Right, so this will run in. We're not using them, so it's gonna ignore it. But yeah, that's a style thing, which is not important. Okay, is the array a variable for int 10? Yes, array, which is an arbitrary name, right? Variable name. Arbitrary name is just the name of our variable. Its data type is an int pointer, and an int pointer is a memory address, and arrays are reference type variables. So we can go ahead and work with those, right? So, right, array indexing, right? Square brackets are offsets. These are calculations based off the memory address of the value of our variable. And then it offsets and takes us to an element type, which is then treated as an integer. All right, we could print out your array number. First element is the first element because we're zero-based like most languages. All right, 25 inside our array. All right, let's say we got something weird being printed out. Change my code slightly and say, oh, okay, our first element is this garbage value, which isn't quite a garbage value, but we'll leave it alone. All right, this is where the debugger is super important. Click the gray bar on the left-hand side, that puts a breakpoint. Or F9 is a shortcut to turn breakpoint on and off. And so when you start Visual Studio with a local debugger, it sees a breakpoint, it's going to run until it hits it, which means you can mouse over and look at the contents of things. Right? Locals variables shows you everything that's in memory, so you can expand various things. You can add watches. If you want to know what the value of pointer is, go in there, type things, and it shows you what the value of pointer is, the value that's being pointed at, data types. Right? As applications become more and more complex, aside from having good logs, you need a good debugger. Logs will hopefully give you a clue to where in the code you need to look so that you can get the debugger up and running and throw data at it and find out why your pasta, is not sticking to the ceiling. So whichever compiler or IDE that you're using, the debugger is your best friend. I recommend you learn how to use the debugger as much as possible because that is going to help you solve most problems. All right, so this is one of the ways that we'll be using pointers in the class. The other way is for creating objects. I just leave it on as data. All right, nodes star X is not a great name. Equals a new node. X is not a great name. Not equals 55, and then we'll spit it out. Oh, look at that. I was smart enough to fix my syntax for me. That was nice. Try to use a dot operator for a pointer. I'm going to show you the code really quickly. All right, there's our variable value 55. So line 33. All right, we have two things going on. One, we declare our variable. X is not a great name. So that's our local variable. Second thing is we're actually allocating the variable by calling the new keyword. New keyword allocates memory for that variable based off of the node data type on the heap, and then tells us where it is in memory. So it's telling us where it is in memory. We need a pointer. Since we have a pointer, we have a slightly different syntax here, which is an arrow. Right? So in Java, you would just use a dot operator and it does the dereference for you. In C++, you use the arrow. It's a dash greater than. That dereferences the object and does the field operation so you can get to the particular field. So this will be one of the areas that's different than Java, as opposed to like Java, you put public int data on everything, and of course use properties and all that fun stuff. But again, encapsulation is not something that we particularly care about. Organizing your stuff into appropriate classes, that's useful, and I'll try to push you in that direction, because having one massive class for everything is not the way to write code. But if it meets the objectives of assignments, then that's fine for this class. Right, so this is why we need to know pointers, because we're going to be using the new keyword a lot for a lot of the things we do, and we need to have a pointer to grab onto that, and then we'll use the arrow syntax to work with the fields and methods that are inside that type. Questions at the moment? Okay. Let's see. Let's do functional notation. Put the link to that in the chat in case you want to be on the page yourself. Grab, copy, paste things, doesn't matter. You don't have to pop on if you don't want to. All right, so functional notation. Here, what we're doing is taking a piece of code and looking at the cost of that code. Essentially, counting the number of operations that it goes through to get the job done. All right, so for any given algorithm, for a data set of size n, an expected amount of work is going to be required to find a solution. All right, so say we have a problem. Find a value in a set of data that is unordered. All right, so do some pseudocode here. Say we have our array of data equals, all right, 0, we'll pretend, well, we should do whatever, 1, 15, 12, 4, 9, 99, 2. Doesn't matter. Int key to search. equals, let's say 7. Right, so in order to solve this problem, we need to test 7 against 1, see if it's a match. Test 7 against 15, repeat, right? So our algorithm, type, compare each element in the set to the search key, starting at the first element. Find a match. We're done. If not, keep looking at the next element until there are no elements uninspected, or we found our match. All right, so we just do a simple for loop. I less than, we'll pretend we have a size variable somewhere. That's tracking how big that array is. If our data set of I matches our key to search, then we've found what we're looking for. And we'll just do a print statement here. Found key to search. Right, at index, whatever. Sort of thing. Otherwise, we might get to the end and just not find the data. I'll leave the negative path off the moment. So what is the cost of this block of code? So our functional notation, so when we analyze a line, right, look at line, identify, identify. Operations being done. And then account. That creates the line total. And account for loops or other types of replication. Types of repetition, causing that code to be evaluated. Evaluated more than once. All right, so let's get some line numbers in here. That's interesting. Let's see. That's not what we want. Okay. Yeah, try to help me out. Well, I'm going to ignore the curly braces because those effectively are not lines of code. There's nothing to execute there. All right, so line 1. We have our for loop. Our operators. Equal sign. All right, the less than operator and the plus plus. All right, so we have our assignment operator, relational operator, and a mathematical operator for increment. The equal sign, right, is evaluated one time regardless of the value or state of size. Less than sign is evaluated size times for all the true results plus one additional time when I is equal to size, right? The one false scenario. Plus is evaluated size times, right? So if size is 0, right? So for example, all right, so for example, size equals 0. All right, I equals 0, I equals 0. one time. I less than size, one time. And then I plus plus, it's going to be 0 times. All right, so it costs us 2 operations to run through the code when the array is empty. Our count of size is 0. There's no useful work to be done here. All right, so we have total operations is 2. How are we doing with that? Okay. All right, let's go ahead and
Sorry,
go
I
up
have a
by
question.
1.
I didn't quite get that. What does the cost means? Like, what are we looking for?
The amount of work that's being done by the code. Right, so as the amount of data increases, the cost of running this code is going to increase. So right now, this is not an ideal search algorithm. Linear search, pretty much the worst search algorithm you could have.
Mhm.
So we want to look at the costs of it and see, okay, are there other ways that we can approach the problem and solve the problem that has a lower cost, lower overhead to get the job done that we'll be asking for it.
Okay, and for the example, when you said that when the size of the array is 0, so it's gonna go to the index 1 once time.
Yeah, so it's not even going to get into the loop because the very first test is false. 0 less than 0 is false.
Okay.
Right, so we hit the initializer once because that doesn't rely on size being anything in particular. We must test once before we get to the body, and our very first test is false.
Okay, and it's not gonna add any index anymore, so it's gonna be 2 operation total.
Right, so the array was cleared out, and then we were asked to search it, and we said we can't find it because someone cleared out the array. For whatever reason, the array is empty at the point in time we try to search it.
Got it, thank you.
Okay, so for our smallest non-empty array, initializing I to 0 is still always going to be 1 time. I less than size. This is going to now be 2 times. I less than size, 0 less than 1 is true, and then 1 less than 1 is false. So this operator is going to be evaluated 2 times. And because we actually enter the body of the loop, I plus plus will be evaluated 1 time. All right, so our total number of operations is just the sum of that 4 times, right? 1 plus 2 plus 1, 4 operations.
I have a question.
Mm-hmm.
So for the second one, the size is 1.
Yep.
So first I equals 0, this is the 1, and then I less than 0, which is true.
No, I less than 1 because the size is 1.
Oh, sorry. So 0 less than 1, so it's gonna 1 time, and then it's gonna add index, so it's another time.
Yep.
And then it's gonna be I equals 1.
Yep.
So, but
yeah, so that's what caused the loop. That's going to cause the loop to stop looping.
so yeah, so but why we don't include I equals 1 times?
It's here. When I becomes 1, so when we run through the code, size is 1.
Mm-hmm.
So we go in the loop, and we're going to be doing this stuff, which we haven't gotten to those lines to analyze.
Mm-hmm.
It does the body, then it comes here, goes to 1, and then it comes back over here, and that's what we've counted. So like there'll be 2 times this relational operator will be evaluated at runtime.
Okay, so when we add 1 index as I equals 1, so we don't go back to the initialize that is I equals 0 and change it to 1.
Yeah, the loop would never end if the code worked like that. Yes, the for loop does not initialize but 1 time. Right, initialization is an initial thing So it should happen at the beginning one time.
Okay.
All right, we're scaling up. Initialization, still only one time. ILS size 11 times. Let me break that down and say 10 plus one time. 10 times, this is gonna be true. So for 0 through 9, we're gonna enter the body of the loop. And then when I becomes 10, that's gonna be the false case. So 0 through 9 inclusive is 10 times we will enter the body of the loop. And it will be 10 times that we increment. I will start at 0 and I will end at 10 when the loop is completed, assuming it doesn't find who we're looking for and exit out. But as it stands right now, this is coded, so there is no early exit. It will find all copies of the key, and every time we find it, we spit out the value. In fact, let me just add a duplicate value in there just for that purpose. Right, so our total operations, 10, 20, 30, 31, 32 times. All right, so our cost is going to increase. If I would continue to increase the amount of work that's being done here, the amount of work is going to also increase along with it. So we're up here to, where did I get that 32 from? That should be 22. Make sure you check my math, because my math occasionally I goof. I try to grab that 10 and add that in there. Fortunately, I have Google to help me with the spelling. I don't have to worry about that one as much. All right, so 10 elements, 22 operations, 20 elements, 42 operations. What we can do here is now abstract our sample size to n, and this term is being driven by whatever that value happens to be. And now we're down to this formula, this particular code block. If there's 1 million elements in the array, we should expect 2 million operations that's basically being sent to the processor to do work. If there's 200 elements in the array, and it's 2 times that, 402 operations of work being sent to the processor. Everyone sort of with me here? All right, so that's how you get the functional notation. That's just our first line. So now let's go ahead and get down to line 2. Line 2, which was our if statement. All right, this has 2 operations. We have the bracket I operation and the equality operation. Right, so freestanding by itself, cost of this line is 2. Right, this line is within the loop body of line 1. Line 1 will cause this line to be evaluated n times. All right, so what we're going to do is we're going to multiply the iterative component by the line component, and we get a cost of 2 times n. All right, so we go back to the code overall. All right, if we have a 5-element array, or however many elements this is, and we're looking for 7. 0 is less than however many elements that is, we go ahead and make the test. Is 1 equal to 7, right? So we offset the array to get to the 1, then we look at the value of 1, compare that to the value of 7, and find out if yeah, you have access to this right now, right? I posted the link in the chat earlier. I'll post it again. So it's on Google Drive right now. Yes, and the link to this is from Canvas. So if you forget, let's swing back to that. Where this is, syllabus page has basically most of our external links in here, whiteboards. Right, and here's all the files that will come as they are created on lecture nights. All right.
Professor,
Yes.
so functional notation means what is the cost of the program?
Yes. The literal how much work this program does for a given data set.
All right, thank you.
All right. So after we've looked at one, I will increment. We'll look at the second element is 15.7. Repeat 12. Right. We look at every single element. And if it happens to be true, we'll spit out. Then it is found in the data set. Right. So line 2 gets hit on every single pass through the body of our loop. All right. So for line 3, it's a little bit more complicated, but we'll look at it in a couple of ways. Because it's an array. Arrays are reference type variables. Right, instar data, it's an instar because arrays are reference type variables. You can't store multiple numbers in one integer. All right, line 3 has numerous operations, all which are the same, right? Extraction, insertion, get my copiers back. 1, 2, 3, 4, 5, right? We won't consider end the next operation. So we have 5 operations, all of which are our double arrow. Right, so freestanding, we had this code by itself. It executes 5 operators. Now we have 2 things to consider here. To consider, as there are 2 parent constructs. First parent is the if decision. The second parent is the loop. Right? The loop will cause line 3 to execute as many as size or n times. The if constraint is pushing that down, possibly as far down as 0. Right, so there's 2 ways that we can approach the data. And so we can approach the workload. In the worst case, what does the data look like? That would cause most amount of work. And for this would be every value in the set is the key value. Or we can look at it in the lightest workload case, where we never find the key. Right, so in the worst case, line 3 is executed. n times, and each time costs 5 operations. So we have 5 times n operations. Right, no work scenario or lightest work scenario, it never is evaluated. When we're looking at how expensive is a function, we're going to look at it in the scenario with the worst case. What's the most amount of work this is going to do? So that's what we're going to approach it as, so we can get that out of the way, because the worst case is what's going to drive our decisions initially. Average case is sometimes also going to be used. Well, as we get to other algorithms, we'll look at those as well, because worst case is typically a rare scenario. And then if it's truly a rare scenario, we don't necessarily always want to use it as a benchmark to compare our different options. All right, let's see. Does it not count that you're having to select an int value from an array? Seems more like work than just comparing. Yeah, I'm counting the array indexing as one operation. And that's a good question, because we could break the code down into smaller parts where we do, right? We could do the math ourselves. We could treat it as a pointer, do an I plus or offset and all that fun stuff, because an indexing operation is actually a complex operation. There's multiple mathematical steps in getting it. Because since we're using C++ as our high-level language, we're not going to worry about those details. It would change the functional notation, the cost of doing an array indexing operation, right? So show up here, right? Is going to be more expensive than just reading the key. And right, we're not counting just reading the variable as an operation either. Right? We're not counting the costs of calling C out, right? Because there's still costs in that. So, and the other thing we can do is we can compile this down to assembly and then look at basically just lines of code, just how many times is each line of code. Because when you get down to the assembly level, right, the commands are far more atomic. Most commands are more consistent with each other, as opposed to things in the high level language where this little bit of code compiles down to multiple statements in assembly, whereas this bit of code pretty much compiles down into register we're looking at, and the equality compiles down to one instruction. The effect that has would just be an extra multiple, right, where we count this as 2 operations. And if we're counting that as 2 operations, then this 10 becomes not there. Right? We count this as 3 operations instead of 2, so it ends up being a multiplicative effect, which as we move this to the next notation, or big O notation for asymptotic notation, see the complexity, all of that stuff gets stripped off anyways. But it's a fair point. And if you're getting really critical on the code, because our application is real time and it's extremely sensitive to every microsecond or nanosecond that elapses, because we're, high frequency trader type thing, and we're in that server that's connected to the fiber wire that goes across the Atlantic, or we're developing software for fighter jets, and right, anything that the pilot does, you need to not go think about it, not go spinning off on a cloud-based call to the cloud and see, should we be doing this? Does it pass validation? Right? It all depends on the requirements of the platform. If you're building a checkers application to run on an Android app somewhere, the user's not going to notice 10 milliseconds here or there. Yeah, well, a millisecond here or there, but we'll start to notice tens of milliseconds. I've got that little article I was mentioning earlier. Let me bring it up so we can talk about that later. What is it called again? I should have opened it earlier so I could have. Not in labs, not in exercises. There, performance. Yeah, so we'll talk about that in a minute. All right, so you have another question. Why would every value in the set being a key value be the most amount of work? Right, each one is the same amount of work for the if statement because we're not exiting as soon as we find an occurrence. The array indexing is more expensive than looking at a literal value. In fact, that is one of the micro optimizations. So this will totally be an aside. As an aside, off topic. Micro optimizations, which you can feel free to Google that. There's all kinds of fun philosophy on that one. Say we do have this code here. Not actually doing it more than once, but let's do something like that. We have a for loop and I equals 0. I less than size, I plus plus. All right, so we have, all right, if array sub I is less than array sub I plus 1, then we're going to do a swap sort of things. It's kind of like prelude to our bubble sort. And temp equals array sub I. Array sub I. Those array sub I plus 1 plus. They're going to find you on the keyboard. Array sub I plus 1 equals temp. And print out a message. Why not? We swapped array sub I and array sub I plus 1. So here we're doing the same operation. And this is one of the things I call out when I'm doing code reviews. Array sub I, right? Let's say is 1. Array sub I, it's still 1. Here, we can't get away with it because we're doing a mutation. We have to put it there. And then we read array sub I plus 1 again, which we've done previously. Here we can't get away with it because we're doing the mutation. And then again, here we can't get rid of it because we've actually changed the state. So these we couldn't copy, right? So if we do things like int left-hand side equals array sub I and int right-hand side array sub I plus 1. In fact, let me do the side by side. Right, the idea being is because accessing the array is expensive and the compiler might be doing this for us anyway, instead of doing repeated operations over and over and over and over again, we do basically caching or buffering of our values. And we can just switch this around. It'll be the same values, RHS and LHS. Right, so I've cut down the number of array operations down by a lot because they are more expensive. Right, so what you could do is you can take both of these code files, create a simple program, compile them down to the assembly, and basically look at how many lines of code are different between the two, and that will give you a better sense of, the cost associated with, standard practice stuff, which I find it to be very rare to do something like I have here in this example, because it's what's classified as a micro optimization. It's sure you might save a picosecond, but you need to do this billions of times before it becomes a redeemable optimization where you actually get benefit for writing the extra code. And this has a side advantage of maybe you're less likely to have bugs by not getting your I's and I+1s offset. Yeah, right. This one does not stop. This one's finding all. Right. So this one does find all. This one finds all occurrences of our key. Yeah, no break keyword in this one. It's not exactly the lab. It's just similar to the lab. All right. Line 3, name it bold. That's that. Okay, now where are we? Oh, okay, we need to take a break. Let's go ahead and take a 7-minute break, refill the water, get a snack, whatever. Yeah, so we'd use a little bit more stack. You'd have those 2 temporary variables, so you're going to use a little bit of stack space. That's a pretty small amount. And usually, to get more speed, you need to throw memory at it. That's often the case. All right, we'll go ahead and go on mute for 7 minutes, so 10 till. We'll come back and we'll keep on smashing the whiteboard around, taking questions. Let's see. All right, we're just going to do some more functional annotation again. Be different. Algorithm, binary search. All right, so binary search algorithm. This is one of many divide and conquer approaches to find a solution in a data set. There is a precondition for the logic to work, that being the data is ordered, specifically sorted in an ascending fashion. The linear search, we eliminate one item at a time by starting from the beginning. With binary search, eliminate half of the set at a time, and we'll do this by starting in the middle. We'll compare the middle element in the set against the search key. If it's not a match, then we'll eliminate lower half the data set if the search key is greater than that middle element. Otherwise, we'll eliminate upper half.
You're talking about the less or greater operator, right?
Yes, less than operator. All right, so let's say our data. Now let's do a table. And 12 is good. All right, so index and round. Let's do round slash index. Right, so round zero, initial state, we have our data and it is sorted. Arbitrary values here. And we're going to search for, we'll just search for the first value, 1. Okay, so what we want to do is find out the middle. Middle is the two boundaries added together, so 0 plus 10 divided by 2. So this is the middle element. So we'll go ahead and look at 18. Compare 1 to 18. We see the 1 is less than 18. Since 1 is less than 18, it is impossible in a sorted data set for 1 to be to the right of 18, right? Transitive math logic there, because 1 is less than 18, it's transitive reflexive, I forget. Less than 19, 25, 29, 31, 35, anyone that could possibly be to the right of 18. So that means we can eliminate. So we did not find a match. So we didn't immediately say, okay, we found it at index 5. So we test to see which way the data could be. So if it's going to exist, it has to exist in the left-hand side set. So what we'll go ahead and do is eliminate all these values. That part of the set can't contain the solution that we're looking for, so we can go ahead and eliminate it. We'll do the same thing again. Our boundaries now is 0 through 4. 0 plus 4 divided by 2 is 2. Our middle element is 9. Do our test. 1 and 9 are not equivalent. So we'll go ahead and eliminate that value and everything to the right. Repeat the same logic again. Range is 0 to 1. 0 plus 1 divided by 2 is 0. Because I'm doing integer math here. And we'll do our comparison, and we found who we're looking for, and we're done. Found our match. I won't copy that much. All right, we'll do a search again. Let's go for something more in the middle. Search for 25. Same thing. 18 and 25 don't match. 25 can't possibly be to the left of 18. So we'll eliminate that half and we'll repeat the process. Our range is now 6 to 10. 6 plus 10, 16. 16 divided by 2 is 8. Our middle element is 29. That is not a match. So we'll go ahead and eliminate. Our range is element 6, 7, 6 plus 7, 13 divided by 2 is 6. So we're looking at 19. That is not a match. Down to looking at one element, and it is a match. We found who we're looking for, and we're good to go. All right, so wherever it is, it will find the data, and it finds it very quickly. All right, so basically it took us.
Sorry, I have a question.
Mhm.
So the list that we have is sorted, yeah? It's from the smallest to the largest. So what happened if like it's unordered?
Algorithm would likely fail most of the time.
So we couldn't use this method then.
Correct. If the data is not sorted, then our logic does not hold. We can't eliminate, right? If one was over here, and I was searching for one, I couldn't eliminate this data set, or 26. Say 26 was, or say 26 was over here, and I'm searching for it. By eliminating the first half, I have erroneously eliminated the value. Right, searching for a value that may not exist in the set. Same thing, we find the middle and eliminate. 11 is less than 18. Find the middle. Oops, that's the wrong letter. And eliminate. All right, find the middle, which is going to be 12. 12. Eliminate. So we eliminated the left-hand side set, not there. We now have no values to look at, in which case the value is not in our data set. All right, eliminated 13 because 11 is less than 12. And we're all done. Some binary search algorithms will give you back a 2's complement, like the C standard library gives you back a 2's complement. Where's the .NET? I forget. Either it's going to give you back -1, indicating their answer is not inside the data set, or possibly a 2's complement to tell you approximately where it would have been, were that number in the data set. So in case you got some sort of fuzzy logic matching, where, all right, maybe 9 or 12 will be good surrogate values and we can use them instead of 11. All right, let me go grab the code for this. Where's my file section? All right, files. Searching, binary search. No, that's HTML. I need to download that. Now we'll walk over the code. And we can step through the code. Let's see. Keep it to the iterative one. Let's lose the recursive one. And we don't need the named exercises. All right. All right, so just a class. Didn't have to be a class, but we have an array. This is where our sorted data would be. All right, so this sample code is just going to randomly populate it, but then it calls sort. So don't worry about sort, it doesn't much matter. Here's our key part, the search, the actual algorithm that we want. Right. We are going to have our upper and lower bound of where we're starting. And then we'll work our way towards that value. Eliminating halves by either pushing the lower bound value up, eliminating a lower half, or pushing the upper boundary value down, thus eliminating an upper half. Right, so step one, get the middle, doing the math like I was just talking about, get our two bounds, which is just 0 and 99 to start. And that gives us, what's that, 49. We'll look at the middle element, do our relational test, and we're either going to update the upper bound, eliminating half of our data, or we're going to manipulate the lower bound, eliminating half of our data. And if we didn't eliminate anything, then we have a match. All right, so just a loop. And a decision construct inside, just like we have with linear search, just the decisioning is a little bit more involved than we had with our linear search. All right, so getting our functional notation here would be the same idea. We'll just isolate ourselves to the search function. Look at operators. All right, this line has two operators, two assignment operators. This line of code, whether the array has 10 elements or 1,000,000 elements, two operations. This line of code or while loop has a single operation. The tricky part now comes into how many times are we going to hit it? All right, so we'll defer that for a second because this line in and of itself is not enough to figure out how many times the code's going to get hit. We have to actually look at the logic inside, which is all constant statements at this point, right? Equal, plus, divide. There's three operations on this line of code. Right, we'll ignore the printing because that is not pertinent to the actual algorithm. That's just for debugging and demonstration. We have our test. This one's a little bit easier to evaluate because all possible paths are covered. Right? Either this is true, or this is true, or this is true. So we can look at this whole block as one entity for the most part, see which is the most expensive and just count that as the cost of this block. Right, and the most expensive path here would be this is false, this is true, and then these operations are hit. Right? And there are alternative paths, but it gets to the point where we need to get a little bit fuzzy or rough in our estimation for how we count all this. Because it gets to be a little bit too heavy in the math side, getting in all the fine combinations, permutations, and things that happen, and we're trying to stay on the algorithm side and what's the cost, not get down into all the nitty-gritty of the math aspect of this. So we can just call this, 1, 2, 3, 4 or 5 operations as this chunk of code. The important thing here is the amount of work that's being done on each iteration of this loop is being cut in half. So if we have, let's say, 100 element list, right? This will take, now see my brain's working on 2, 4, 8, 16, 32, 64, 7 iterations, 200 element list. This will take about 8 iterations. Do a bunch of copy paste here, and I'll keep doubling my list size. And I'm only going to increment my iterations by 1 each time we do this, because base 2 cutting in half, double the size of the list, just one test. Right, say we had a 1600 element list. The very first test brings us down to 800 element list of where the answer might be. Each test keeps cutting the work in half. That's why as the work doubles, it's only going up by 1 more iteration until we get to 1 million, which is going to be about 20 iterations. 1 billion, be about 30 iterations. All right, if we want to go up to 1 trillion, looking at 40 iterations. That's because 2 to the 10 is 1 case. That's why it's going up by 10. Right? Went up by 1,000, went by 1,000 to the 10 is 1024. So you go by 10 iterations. And so binary search is pretty good at its job. The only caveat there is the data has to be sorted. So if you have 1 trillion records that are unsorted, yeah, that's going to be your big problem, is getting that data into a sorted state, because that's a massive data set. And there are definitely data sets out there that are on that scale. All right, so our costs here are getting quite complicated. And this is going to be well beyond, I wouldn't ask you to tell me what the functional cost of this is, because there's too much coupling between the pieces. I'll post some examples later of simple examples. What's the cost of this code? Because functional notation is just going to be a stepping stone to big O notation. Disks are better at sequential reading. First, better than what at sequential reading? Because I would say RAM's better at sequential reading than disks are. But disks are definitely tend to be well suited at sequential reading. It actually depends. If you're talking about a physical disk, sometimes they spin faster than the read head can read all the data. So actually has to wait for evolution. So they actually separate the data on the sectors so the read head can't catch up to the spin speed. But that's hardware and well beyond our scope. I'm sure I spelled this wrong. Asymptotic notation. There are several notations. There is big O. We go some sort of expression. And there's omega and theta and variance as well. We're going to stick with just big O. Right, you can go ahead and delve into the others on your own. That's getting too precise in the math. That's beyond our purposes. And so big O, which we're going to be using throughout the semester for probably 70 to 80% of the things we're talking about, right, is a measurement of the complexity of an algorithm. Algorithm in time or space. Usually, we're going to concern ourselves with time. It takes a worst case scenario approach as default. What does the data look like? Such that the most amount of work is being done to get an answer. And important things to remember. Finding that the data does not exist is an answer or solution. Right? It's just like -1. -1 is a valid answer. It may not be what we want, but it's valid. All right, one of the things is we do use, there's going to be some approximation is done where we use the functional cost.
Professor, I do have a quick question.
Yep.
So like I know like for most arrays, we always return -1 if there is no value. But if you're doing something like you have an array of like like objects or something,
Mhm.
and they have like a balance, and that balance could be negative, what would you return?
Well, balance is an internal value. So I would return the account and not the balance so that you can see, okay, I got an account back.
Okay, but
And
that's
then-
fair. But like, I understand that was like that was just a bad like example. But like, if you were doing
Yes.
numbers that were negative,
Then I would use the nullable type and return back the nullable equivalent. Like in C#
Okay.
you can use nullable type, so you return back null. Null indicates not found. Because now, yeah, because it's a legitimate problem. Negative is a potentially valid answer in the solution set, so you need a null equivalent. And if a null equivalent is not available, then you need a sentinel value, such as like -2 billion, the smallest possible, if using integers. -2 billion is the smallest possible number that you could have in just eliminate as a valid value that an account could have, because we're not going to let anyone overdraft $2 billion, sort of thing.
all right, thank you.
All right, so we're going to use the functional notation of the algorithm and simplify it by only considering the fastest growing terms and eliminating coefficient of the remaining term. All right, so before we had linear search. All right, it's functional notation 2n plus 2. We want to get this to big O. All right, so step 1, 2n is the fastest growing term. So we'll drop the term 2. The coefficient two is then dropped, and we're left with n, and that is just wrapped as the expression inside of our big O. All right, so we get our big O of n, and this is a linear growth pattern. Yeah, linear search, linear growth pattern. That being an intentional association. As the amount of work grows, which is the size of the data set, cost of the algorithm grows proportionally. All right, so let me find my big O cheat sheet. Let's see, it should be in modules. All right, so module is a big section here, big O, big O, big O. One of these, we have a big O cheat sheet, which has a nice chart on it, showing us our various time complexities. Now, one thing to point for this chart, the diagonal, this is not a linear scale. This was a linear scale on this chart. ON would be the diagonal. So to keep these lines somewhat separated, they've got a non-linear scale on this chart. So down here, all the way at the bottom, these constant time operations, big O1. Big O1's constant time basically means you can have 1,000,000 elements. The algorithm is going to take the same amount of time as 1,000 elements as it takes with 2 elements type thing, you know, roughly. Then we'll have logarithm, which we're going to have with our binary search. It's pretty fast. It's pretty close to constant time, but it's not quite there. And linear, which we'll see often, it's a straight line. And then n log n, it's a little bit of a curve going up there. N squared, things start to get bad quickly. Base 2 to the end, things get bad very fast. And in factorial, you just forget about it. Any sample size elements, things are just going to get really bad, really, really, really fast. And just have a little table here telling you that the expected time complexity of things. Space complexity is on the right. Right? Arrays, right? Constant access. They're using the theta notation, so it's a little squiggly inside the O. So those are actually thetas. For our purpose, we treat that as a big O anyways, like we have here. Constant time. Theta is just more of a, this is actually the cost instead of big O roughing the numbers up a little bit. All right, so other linear notations. We have Fn equals 5n plus 5. Our big O is going to be the same thing. It's going to be big O, and f of n is equal to 1,000. 111 plus 200,000. Do this just like calculus. As n grows large, just like as h grows large, lesser terms, there's a value, there's an inflection point at which n becomes the driver. So it's a small data set. This cost here is going to be enormous and we're going to feel it. But if it's a million elements, 20,000 falls away really quickly because now this term is a billion. 20,000 against a billion becomes insignificant sort of thing. Binary search. All right, this one has a big O, log n. As we saw before, when you cut a problem by a fractional amount instead of by a fixed amount like linear search does, you get a logarithmic scale. So if we're cutting by thirds, so cutting in halves gives us base 2 log. Cutting in thirds gives us base 3 log. Right? If we were cutting in tenths, then we have base 10 log, right? Regular log, right? So the LG just means base 2. It doesn't really much matter because it's a constant coefficient, base 2 versus base 10, and coefficients, we go strips away anyways. And so if we start getting more complex expression, 5n plus 5 plus 3 log n type thing. Our fastest growing term is the 5n. So this goes to 5n, which then goes to big O of n. If we have more expensive operations, right, plus 3, natural log, base log, 2 log, log n plus n times n. Our fastest growing term here is now n times n, or n, also known as n squared. Let's put a coefficient is just 1. Not really anything to put there. That's not what I want to do. Still not what I want to do. All right, what's my shortcut? Whatever, n times n. Which means we're getting to that scale where the cost of the algorithm is going to grow quickly. 100 elements, right? If we do a comparison, let's compare these 3 growth rates. Big O1, which is constant, big O log n. No, I didn't do constant, add linear. Log n and big O n times n. Let me put these in order. And our n squared. All right. log n's approximately 4, linear is 10, n squared's 100. As these go up, 7, 100, 10,000. Workload is going to be growing at much different scale. All right, getting up to 1 million. 10K. No, what are we there? Let's see this. 2 is that 8. Whatever. Someone can fix my math for me. I'm gonna say that's about 13, since my brain doesn't want to do math. And we're there, 100 million operations to get the work done. All right, so basically, if we have 3 algorithms that can all solve the problem, one algorithm falls under the n squared, one falls under linear, and one falls over logarithmic. Unless there's some sort of other hidden cost, we are going to want to choose the one that has the fastest O notation, the best time complexity. Otherwise, things get really, really expensive. But if we're not dealing with any data sets of any size, but I'm saying that's the days of the week or the days of the, or the months of the year, and I need to sort those, right? 7 elements, 12 elements. Those are so small data sets that it doesn't really much matter, because there's not enough work being done to justify the cost.
Professor?
Yeah.
I have a question. How did you find the log n for the 10,000?
It's just that one I just know off the top of my head, because 2 to the 10 is 1024. But you could do, oh, where do they do the log in here? Whatever the math is for log base 2. This calculator doesn't, let's see. Grab a calculator, do it. No, that's not what I want. It's the math. You don't have to worry about that math. But the log base 2. There we are, log xy. Okay. Not too sure. But yeah, okay, you'll want to use a calculator for that, but I'm not going to have any kind of math that's that complex on
But
the test,
why the base of the log is 2? So,
because we're cutting it in half.
oh, okay.
Right, we're not cutting it by 10.
Thank you.
Okay, so why data structures? Why do I have to take data structures to get a computer science degree? And this article was from a long time ago, so the link has since disappeared, gone. You can probably find the research there, but they're comparing, right? Users tend to be impatient, right? You click on a link and nothing happens, like, oh, did I click on it? Or why isn't anything happening? Click on it again. Right, so in milliseconds, right, 100 milliseconds of extra load time on their site for pages causes a 1% drop in sales. I don't know how many billions of dollars Amazon did last year, but 1% is a small number. But when you're talking about $1 billion, that's $1 million. So it's worth them to spend $250,000 to upgrade their data storage system, if that's going to translate into a tick or two of performance improvements, because the faster, you anticipate impatient users. I mean, a lot of sites are like, don't click the back button, don't click the next button, because you're going to break. They basically have to give the instructions to the users to be patient, because they know it's going to be an expensive process, right? You're doing an online payment transaction, that's got to jump through a bunch of hoops, a bunch of systems, got to go through a bunch of banks and the credit card brands and all kinds of other stuff before it makes its way back to your browser and say, yeah, it's approved or declined type thing. So they know there's going to be seconds involved. So they say, just give it a moment or two so we can let things flow through. Right, 500 milliseconds, 20% fewer searches. If Google gets 20% less volume, that would be a massive So when you're dealing with companies that are doing data at scale, they're going to be particularly sensitive to the algorithms being used and how efficient they are. The other thing, like I mentioned earlier, real-time systems, if right, you're playing a game and you got 20 millisecond ping and your friend's got a 30 millisecond ping, you have a natural advantage over them because things are going to happen so much faster for you that you actually see them where they are, as opposed to a 300 millisecond lag because you're on a satellite connection, and people are basically warping around on the screen because most online gaming like that is pretty close to real-time systems. So that'd be one of the other common domains where there's only so much you can do about the network speed, but once the data gets into the machine, you want to be able to process it as quickly as possible so you can get responses moving back out. Because if you have to, oh, I don't have this information, I got to go hit the database. And then I got to do a bunch of data compaction on that data, and then I got to send it back out. Those costs are going to lead to user frustration, which means you're going to lose users, which means your revenue is going to drop. Right, and then you got the fighter jet system or a Boeing plane. Right, if most planes are fly by wire, which means electrical communication between circuits and motors and actuators and all that fun stuff. And if the pilot wants to deploy flaps and there's latency, right, that can result in dire consequences if the system is not doing things quickly, where a fighter jet is going to be more, or the most important in that group. But if you're going to work for a defense contractor or Boeing or something like that, they're going to put a lot of scrutiny on the algorithms used, right? Security, performance, all that fun stuff. So that's where the algorithms that we look at and the data structures that we discuss would come into play. Otherwise, most of the time we're going to be, which we get to at the end of the semester, dictionaries for data storage because it tends to be really quick, and various other algorithms are going to be very, very commonplace for the usual in and out client server applications, right? You're signing up for Facebook, you're reading posts on whatever app, you're playing an app on your phone where at the end it records your score and saves it to the cloud, your account, so that you can see your stuff on the browser and other devices, all that fun stuff. All right, let's see. Let's talk about stacks and queues. Where are we? There we are. Right, we are starting off with various linear data structures because they are the simplest data structures. Right, so stacks and queues. Queues are both linear data structures. Underneath, you'll find either an array or a linked-based structure to store the data. And the stack or queue type will wrap around that data a set of operations that are enforced for how we access the data. All right, so stack. This is going to be a first in, last out, or the reverse. Last in, first out data structure. When data is added to the set, it's added on top of the already existing data. When data is removed, it is removed from the top of the stack. Adding is called push, and removing is called pop. All right, so if we have it's there. These are just going to be our stack states. So we have the operation push 10, push 20, pop, push 30, for example. So our initial state, put 10 at the bottom. 10 exists already, so when we push 20, and that goes on top. When we do a pop, it's going to cause 20 to be removed. So 20 leaves the system. And when we push again, push on whatever data is already existing. All right, so most common use of the stack, again, it's like a stack of plates, dishes, whatever. The runtime stack. All right, we start at main. Start at the main method function, and that's the bottom of the stack. We call a function stack frame is allocated and pushed on top of main. If that function makes a function call, that frame is pushed on top. On top of that one, the function completes. That frame is popped off by changing the stack counter. All right, so you probably talked about this one previously when talking about functions. You learn about functions, learn about how parameter passing and all that stuff goes along. This is that concept. We're also going to make use of this in a reverse Polish in program 1, so we will be swinging back into this one later. The queue, right, aka line. Right, so when adding data to the set, we add it to the end of the line or end of the queue, known as end queuing. And I forgot one of those U's, too many U's. All right. As we remove data, we remove it from the front of the line. All right, so this is a first in, first out, or a last in, last out pattern. All right, so it's basically essentially we're ordered by time. First to arrive is the first to be served, and the last is the last. Right, so job algorithms such as managing all the processes running in the computer will typically use a queue to work through the data. All right, job 1 comes along, gets added, job 2, job 3. All right, as resources are available. Pull a job in the queue and do work on it. If that job is incomplete, and we'll unqueue it again. All right, print queues. Same idea as print jobs show up. First to get there is the first printed. Right, assuming there aren't any priority systems in place, which are certainly something that can be put into place. All right, so we're going to start getting into code or how we can start implementing these. And there's going to be two options, and those basic options are you're either array-based or you're link-based, and on occasion some structures will do a blend of array and link-based constructs. Right, so we should be familiar with arrays. Right? And arrays, once created, have a fixed size, and requires additional code to resize them versus link-based. Link-based, which are dynamic in nature, grow as needed. And require and whatever. Oops. So the array-based stack, what we can do is just create an array. And let's say we just size it as 10. And let's do another row here. What we can do is we have a variable called top. And this tracks where the top of the stack is. When we do a push, some data, go ahead and set our array state at the top to be equal to that data, and then just move the top up one. So if we push 25, this gives us a stack state as so, and the top is now equal to 1. So we need to go ahead and push again. We'll go to index 1, set the value to 50, and then increase the top to 2. When we want to go ahead and pop, sends data back. We're going to go ahead and decrement the top first. Decrement the top. Stop at Google. Minus, minus. And then we return back the value from the stack at that position. So
And
if
you
we go
return
ahead,
back, the stack will be 50, right, Professor?
yeah, so we'll return back 50. So our state before the pop, so we'll go ahead and do the pop. Right, so the pop is going to yield back 50. So we come along, our top is at 2, so it's pointing to the cell. We're going to decrement it down to 50, and then we'll read that value and we'll send it back. And that will bring us back to the state where 50 is more or less gone. Most implementations, it's going to leave the stack state a little bit dirty where 50 is still there, but the top of the stack is at 1. So the next time there's a push, it's just going to overwrite the contents. All right, so if the values on this stack were actually sensitive data values, you wouldn't want to add additional code that actually clears out the value in there.
And would the value of the array be now be 1 at position 1?
Yes,
Because you popped
so
it, right?
right, so the top is here. So top is 1. So that
Okay.
if we do another push, it's going
Right.
to push here.
Uh-huh.
If we do another pop, top will go down to 0, and then we can remove the value.
Right.
Right. So if we pop again, that's going to yield back 25 because the top's going to go to 0 first. So decrement top to 0. And then we'll pull back the value that's at 0, and then the stack is back to an empty state.
So you're at the beginning of the array then.
Yes.
Yeah.
So if we're to try to do a pop now, we should send back an error saying can't take a value from an empty collection. If we want to do a push, we push at 0, and the top goes up. All right, so if we want to push a new value, push 17, we write the value at the present top, which is 0, and then the top goes to 1. Right, so we can grow and shrink. As long as we only get up to 10 elements, the array is going to work very well, which is how the runtime stack works. The runtime stack is an allocation of the RAM memory space, and it's treated purely as an array. And stack frames grow up, stack frames go down. You got recursion going out of whack, and you get your lovely stack overflow exception. Yeah, so with this way of doing it, the top is the first available space. The other way you can do it, you can have the top be at -1, in which case push, you'll pre-increment the value and then pull it, and then the pop will post-decrement the value. So it's the same thing, you're just handling it in a slightly different way. They're both more or less the same. I like 0 indicating an empty stack because 0 null, right? That's empty. So I like 0. -1 is also a valid thing. Let me go ahead and there's files. Right, let's see. I don't think I actually have stacking. Oh, yeah, there's a stack. Int stack array.
Professor?
Mhm.
Real quick, would these algorithms be easier to do in Python? Like,
It should be the same.
Oh.
Now, Python likes to give you a lot of helpers where if you're going to implement it in Python, it'd be about the same. If you wanted to use a stack in Python, like most languages, there's probably already a library type called stack that you can just call push and pop on. Or like C++, you just use a vector and push back, pop front, right? So you can very easily use the vector type and create a wrapper for a stack or create a wrapper for a queue if they don't already have it, and just call the library functions. In this class, since we're concerning ourselves with the algorithm, we are implementing those ourselves. We are always creating the types. The only areas where we're not doing that is with IO, right? Or strings. Anything with the primitive data itself, we'll use library functions for. But all the algorithm data structures, we're implementing the code ourselves so that we know how the wheels work, so that when the next language comes around and we're working for the company that's developing the language, we're creating the libraries. Right? I can't, if I'm creating p cubed, which is based off the Python syntax but doesn't use any of the Python libraries, and I need to provide libraries for the developers that are going to use p cubed, I need to generate the libraries, right? So basically we're taking a reflector and digging into the Python library and seeing how it works, sort of thing, but in a stripped down, simplified version.
See, so there isn't like a specific language that is more attuned to I guess certain types of algorithms. If it works, it works.
Yeah, all languages support all the algorithms. Just a question whether or not that language is already built in first party support for that. So some library developers that are the company's libraries will have libraries that do that, or you might find a NuGet package, for example, is you get a third-party developer that adds the additional data structures and algorithms. Like for like a long time, .NET didn't have most of these things, but in later versions, they got around to adding libraries to support several of these. So for a long time, if you want to do tree structures in .NET, you have to implement them yourself until they actually got around to the point. I think they have I think they have a couple of trees implemented. But as far as Python, right, the language Python, creating the structures and all that stuff and the code, it's more or less the same.
Gotcha. Thank you.
Right, so the actual code in the file section under linear structures or push pop, right? There's really not a whole lot to the code. We have the extra tests. Make sure that there's something in the stack, right? Making sure there's room for values, making sure there's a value to pop. Otherwise, that's pretty much all there is to array-based stack code. It's very simple. When it comes to a queue, yeah, in this implementation, all right, okay. With a queue, things get a little bit trickier. Because it's going to need to leverage a circular array. Right, so we're going to track both the front and the back. And the count variable is a good idea as well. Right, so as we enqueue some data, right, we'll go ahead and dump the values in, right, the queue, the back, was the data sort thing, and increment the back. But here we can't just increment it. We need to tell it to wrap around. And then we need to normalize the back, right? So the back is greater than our size of the array. We need to set it back to 0. And that makes the array circular. DQ and count plus plus, because count is very helpful with a queue. DQ, which is going to yield the data back. Same idea, this time with the front. Right, so we can grab our value, data. Keep things separate here. Here's Q of the front. Then we need to increment the front. And if the front is too big, or alternatively, we can just say front modulo equals size of the table. Wrap it around. So this sets us back to 0 if the front gets to the table size. Right, return the data sort of thing. So let's get our Q. All right, and we'll just go ahead and have front back here at the beginning. So when we go ahead and enqueue, you know what, whatever, 92. Go to the back, drop 92, and we move them back down where it is in the array. Yeah, that's probably a good idea to hold that. All right, so the back move, the front was left undone. Go ahead and keep on enqueuing more values. 74. 74 goes to the back. And we will move the back over. Rinse and repeat. Change my spacing here. Oops. A little bit. NQ 25. 25 goes to where our back indicator is at the moment, and then moves itself along. And we want to go ahead and DQ. Pull from the front, 92 out. Your question about pause is a Windows command. And so because using a Mac, it doesn't work. Just strip that system call out and then that'll get rid of your problem. All right, so we'll go to our queue. Go to where the front is, pull 92 out. And move the front on up. Keep on tracking. So the front, when the front gets to the back, either we're at a one element state or we're in an empty state. That's where the count is helpful. But eventually the values will push to the end. All right, several operations later. 99, 18, whatever arbitrary values. 74 and 94, and they're back. Wraps around to the front. Right, so this is where the next insertion happens. Right, so the back and the front values will wrap around to 0 as NQing and DQing happen. Right, this is treating the array as a circular array where after the last element, we have the first element.
Professor,
Yes.
what is this used for again?
This would be like job queues or print queues. Right. So for example, a printer queues, they have memory on the printer and it has so much space. So it can only handle so many jobs. So if you got a shared network computer and you, like in a computer lab and you got 20 people who want to print, all those jobs will be sent or tried to be sent to the print queue. Right. So it's dealing with a fixed base memory allocation within the system. So it's got so many job slots and or memory, depending on the size of the job, to hold on to these data points. And it's just going to keep reusing that memory over and over and over again.
I see. That makes sense. Thank you.
Yeah, so most of the time when you have in a queue, it's going to be linked based because, and both of these are most likely going to be linked based because links based have the option of unbounded growth, which we'll see when we talk about linked lists. But when you're in an application domain where space is at a premium, then you might have to code for the space bounded applications and choose to use arrays because an array is always going to be more compact. Well, for an equivalent number of elements, an array is always going to be more compact than a linked structure. All right, let's see. Let's go ahead and take a 5-minute break, and then we'll talk about singly linked lists briefly, and then we'll talk about lab stuff, and then we will move on to the wait list. So take 5 minutes, and we'll come back right about the top of the hour. Singly linked lists. All right, so I've been doing these little nodes classes earlier in the night, and that was a preamble to these. So it's a node-based structure. The node holds onto the data of interest and a pointer to the next node in the set. And makes the node a self-referential type. It could point back to itself if needed, and a circular list would do so if there were just the one element. All right, so data section and a node star would be what that looks like. So there are gonna be a few operations. Data and link. All right, so one of the steps we'd often do is be creating the node. The node. All right, so we have a node star. That equals new node type thing. Node data equals some values. And node next equals null. All right, next being the typical name of the link. Names, of course, arbitrary, can be named whatever you want. Okay, Google's freaking out on me. Okay, let's unzoom. And it's still doing weird stuff. All right, it's fun. Hopefully it's saved. Not so much. All right. It did save. Okay. Just looks very strange over here. Interesting.
You can insert it.
There we go. I just needed to do something to cause a state change. And we're good to go. All right. So building a list. We have 3 places where we can add data. Either at the beginning, the end, or in the middle. So the list itself will want one or more named nodes where these nodes track interesting locations of the list. We'll at least want to track one end and may also want to track the opposite end. Again, names are arbitrary. I can type them. arbitrary. So we'll just go ahead and call them left side and right side. So adding to left side. If the list is empty. Right, as our initial state case, when we create the list, there are no data points. The list would start off empty. Just create the node and set that node to be left side. Right, so add to left 15. Go ahead and create our node. Equals our new node, and we'll look at the helper constructor that does the job of initializing everything for us. And then we'll say left side was not. All right, if the list is not empty, create the node as before, and that node will link to the existing node, making new node the left side. All right, so we'll add to left again. Say it's 25. Create the node. We will go ahead and set that node's next pointer to be equal to our existing left side, and then make that node equal to left side. And all this, which can be collapsed down. So let's go ahead and add a visual, what we have here. Let's try to do it to me again. All right. All right, so we created 15 and it doesn't link to anything, so we'll leave that blank. I forgot my label. This is what we'll know as the left side. All right, it's just a pointer pointing to this particular node. Come along. We have our existing left side. Create our new node with the value 25. And then we will link that node to the existing left side. All right, in fact, let me break this down into the steps. All right, first step, we created the new node, which we called node. Then we linked node to our existing left side. And then we say that node is the left side. Let me double check my code, make sure I didn't reverse things. Sometimes I'm going too fast and I swap them. Oh, my internet's doing great tonight.
That
it's
node is
Google.
pointing to the left side, right? Correct?
Yeah, I need to double check, make sure I got left side on the left side, not.
Okay.
I think I'm going to reverse that in the code. All right, duplicate, see if we can go around the problem. Yep, totally got this reversed. There we go. And here it is. Right, so step one was creating the node. Step two was linking the new node to our existing list. And then step 3 was moving left side to represent the front of the list, top of the list, head of the list, or different names we might call this. Add to right. Add to right. If we just have a single name node, this becomes an iterative problem where we start at left side, and then work our way to the end, then attach the node. Since that's a linear time complexity, what we can do is throw a bit of memory at it and make the problem we go of 1. So we introduce the right side node. All right, so add to right side. Passes data. So in this situation, we know we have 2 pointers to account for, and we would actually need to do that over here with add to left, because the very, very first add, the left and the right would all be the same node, but keeping it brief for the moment. All right, so we still need to create the node as usual. All right, if the list is empty, set left side and right side to the node. All right, if the list is otherwise, go ahead and set the right side next equal to our new node, nod. And then we'll go ahead and there's 2 ways we can do this. We can say right side equals right side next, or we could just say that right side equals nod, because both right side next and nod are equivalent because of step A here. So they're both representing the same location in memory. So they're both quite capable of making the assignment. Okay, so we'll have a similar set. Well, let's copy the first one. So we'll add 22. Add to right side. And basically all we need to do for this one is add in our right side. Right side, left side, and we're good to go. The next data point comes along. 42, 43, whatever. We'll do as we did before with the Simpsons, we're adding the right side. And we'll move that around. And let's see, what were my data points? It was 22. This one was 43. Let me double check. I actually changed. Did not. Data point. Let's get those to line up. Okay, so we've created our node. Something we do whichever way we're going to go. Then we'll go ahead and do our linking. When we're setting links, the general rule of thumb is set links that are null first, because we're going to get into situations when we get to a multi-linked node structure where we might need the values of those links in a future step. So it's best to set those that are null first. All right, so we set our link. And then we can go ahead and move the right side down. And so the code is largely similar for both ways of adding. It's just a difference of which named pointer that we are going to manipulate. All right, so next step. And we're going to defer adding to the middle to later. So for now, deleting. Same story, 3 places. The left, middle, or back, and middle will also be deferred. All right, so delete from left. Since we're doing C++ and we're not using any of the advanced language features for memory management, if we knew an object, it is our job to delete an object. So that'd be one of the other differences between Java, C++, or Java and .NET. They both have built-in garbage collectors that are automatically there for you. You don't have to do any special syntax or any of that fun stuff or special types or GC new or any of that. We're just going to be using our classic new keyword. And if we know we're done with the object, at some point down the line, we'll call the delete keyword. So we're going to encompass that in that as well here. So we're going to grab the data from left side, because when we're pulling from the list, we generally expect the data that was in the node to be an output of it. We want a temp pointer. Set to left side. Right, this is for our cleanup. Then we want to slide the left side down towards its next pointer. And we can go ahead and do our delete of the data and then of the node and then return the data back. Okay, so we'll start with our existing list that has 2 data points. And we will start some deleting. Can go away. All right, so we'll have temp. Temp will go ahead and track the beginning of the list so that we can delete it later. All right, temporary variable also grab onto 22 so we can send that back later. All right, so those first 2 steps is just setting local variables. Next step was the slide. Try that again. Left side is going to be equal to the pointer, which is the same thing as this node. And that slides it over. And then lastly, we'll call the delete, causing temp to get blown away, freed up. And then we've deleted. And if we delete again, all right, so we'll go ahead and do a delete, which yields back 22. Delete again. End up with an empty list. 1 second. All right, so we'll delete one more time, which will yield back our 43. So our initial state is a 1-node list. We will set temp as we did before. And our return value, so we can grab on to the 43. And the left side and right side will just be set to null. So we'll end up with just left side, right side. Both of which are just set to null. So I'll actually even, I guess I'll do a circled line through it. All right, they are now set to null, indicating an empty list. Leading from right side. Right, this is not well supported in the singly linked list, as we need to update the right side pointer to be the node just to its left. And we also need to update that node's pointer, node's next pointer, to null, which means we have to start all the way at the left, iterate to one before last node, then we can manipulate pointers. All right, so since it's not an operation that's well suited to a single linked list, I'm just gonna leave it at that. When we get to a double linked list, deleting from the right hand side is more supported and useful. So some notes here. One, repeatedly adding to the left side is equivalent to push for a stack. Deleting from the left side is equivalent to pop for a stack. Adding to the right side is equivalent to NQ, and removing from the left side is also equivalent to DQ. And so those basic operations that we just talked about here is what we'll start to use to implement link-based stacks and queues, which we'll spend more time next week talking about it more, because link-based data structure is abstract. So talking about abstract, a warning about this course, it's a little bit of a fight between this course and assembly, for which is the more difficult course material, right? Assembly is complex because you're so close to the hardware that the instructions are so small. Yeah, so DQ and pop were effectively the same code. Pop would be a little bit different because with the stack, you don't need right-hand side, whereas Q, you do need right-hand side, so the code will be a little bit different, but the intrinsic operation is the same. You just have less to worry about with pop than you do with DQ. Right, so pretty much this entire course is an abstract nature. These, in fact, these data types are just abstract data types. And when we talk about a stack is an abstract data type where it just tells you it supports push, it supports pop. Push should be a constant time operation. Pop should be a constant time operation. You are free to implement it however you want. So pretty much all the things that we're starting from are starting from an abstract place. So everyone absorbs information differently, and this is one of the subject areas in computer science that's going to be more of a brain stretching. So you have to work on stretching the brain up, down, left, right to try to get the data to sink in. On that note, if you find interesting links that you want to share with the class, you think that help. Yeah, shifting gears. Yeah, we're starting in third gear with this class. And the linear scale is the easier stuff. We're going to first two sections are linear, then we'll get into trees, which is a nonlinear structure, then we'll get into graphs, which is even more nonlinear, and then we'll actually swing back to some linear constructs at the end. But the best way is to visualize, right? Do the drawings like I'm doing here. Draw the data structure out. Don't try to see what's in the list. Just in your mind. As you're trying to step through what the computer is doing, get a piece of paper, pencil, draw out what it should be doing at the same time, and then have the code printed out. Do the operation on paper, put the data in your program and print out and see that it is lining up. And you want to start small. Always start small. You want an empty list, print it out. A list with one node, print it out. Don't try to like do a lab and then build out 20 items and then print out the tree or the list or the stack or whatever it is and try to make sense of it at that point. And now you're dealing with too much data. You want to keep the data sets as small as possible and then grow them as small as possible. And as you start growing it, you can see where there might be a little hiccups in it, where it worked fine when it was small, but it failed at the end because it wasn't iterating properly, or the state of the list wasn't quite what it should have been because you didn't quite attach the links correctly. Okay, so that's going to be all for lecture tonight. I just want to point you in the direction of the labs, which of course the due dates are still flexible. We're really just on the arrays stuff, is what we've covered in class IO, right? String stream. Next week, we will talk about different ways of code. And I do have in files, right, in the string section, very basic string streams. There's different ways of breaking strings apart. So you can check out these code files. But string stream is built for the purpose of tokenizing strings, just like strtoc for ASCII. Yeah, so there's no late penalties, but please don't wait until penalties start applying, because you can resubmit your assignments. If you turn in and it's wrong, like some people did dynamic array labs wrong and got half credit, you can fix it and resubmit it. And if you've submitted it still before the due date, you can still get full credit, even though the first submission was wrong. And as a general strategy, if your solution is close to or significant and you're running out of time, the due date is upon you, you want to turn it in. Get as many points as you can possible for what you have so far and backfill and get partial credit on the missing points. All right, so that's just as a general strategy for how the late penalty works, right? You get 70% complete and you get 7% of the solution, and then 3 days later, you get the other 3% done, and you can get still get 95% on it instead of waiting 3 days later and turning in. Now you got 70, 80% because of the late penalty on the full value. Simple array and dynamic arrays. Right, simple array, pretty much like what we did in the notes, and then just read it in from the keyboard instead of it being hard-coded. And then the difference with dynamic array is you need to use the new keyword. The new keyword makes it heap allocated, which also means you need a pointer to track it, right? 3 of these first 4 labs are code levels that you should hopefully already know how to do. Before us even talking about it, right? See, I have 20 of you, 21 of you have already submitted this one, right? 44 of you have submitted this one. So over half the class has already got it. So try not to wait, because there are still more labs coming, and where we are definitely lab heavy in the first third of the class.
Professor?
Yep.
So array query, it's gonna be due tomorrow night.
The due dates are really, nothing's really due until the 5th, February 5th, because if you turn in any time between now and then, it's worth the same.
Okay, got it. Thank
But
you.
we've been talking about stacks and queues. So these stacks and queue items are things that you can try to start attempting. Again, if you go to the files step. A lot of the pieces of code that you need are already in here if you're getting stuck, right? We've got int q, we've got, right here, this one's link-based queues, so we will be swinging back to this code later because we're good on time tonight. Leave at least a few minutes for trying to attempt the labs and then dealing with the wait list. And the next time be pretty much the same as this time, except without the first 45 minutes being roll call and all that other fun stuff. See that the head count shrunk by 1, and there's still 3 no-shows. I assume everyone that's here at the moment was here and it, got their name down on the roll call, and no one showed up late or was not around at the moment when I called the the roll call. Okay, that's all for lecture tonight. Any last questions before I go to the wait list? So everyone on the wait list, you need to stick around. Everyone on the wait list, go ahead and rest, read, play some games, watch TV, whatever. For stacks and queues, when you ask to return a number, you mean yes. Well, you don't have to actually, you're removing a value from the array. Whether or not you set that value in the array to 0 or something, that doesn't much matter.
Thank you, Professor.
Thanks, Professor.
Yeah, all right.
Thank you,
Good
Professor.
night. Good night, enrolled students. Gary, you can stop the recording and we're going to move on